better. So I had a question there related to the coursework and your assignment. So the question's about data. A lot of the time you can find data yourselves. Okay? You can get it from free online sources. So, for example, the Federal Reserve in the US, the FRED database, they have all sorts of information about credit spreads and bond yields. There's an awful lot of macroeconomic indicators that you could look at using. Then another source of data is exchange-traded funds. Okay, so a lot of major indexes, they have exchange-traded funds that track them. Okay, so whereas the index itself, you might have to get it from Bloomberg or Thomson Reuters, you could get an ETF that tracks that index from Yahoo Finance. Okay? So you can get a lot of things just on freely available websites. You can get an awful lot of data. And then also, sometimes researchers release their data. So Robert Schiller, for example, he provides data that he used in his papers. So he has things like the dividend yield on the S&P 500, inflation rates, things like that. And you can just download a spreadsheet from his webpage. Kenneth French, where you get the Farmer French factors from, he has an array of different portfolio returns that he calculates from his research, and they're all available, and you can download them freely. Having said that, the university has extensive commercial data sets, okay, that they pay a lot of money for. So Bloomberg is one of them. Reuters, Thomson Reuters Data Stream is another one, which is in the library. So there's also WRDS, which is words, and there's benchmarks available through WRDS. Okay, so to get access to WRDS, you just Google WRDS, sign up. You know, you say you're from the University of Southampton, use your University of Southampton login, and you can see all the data down the left. So I'm not going to teach you how to access all these different data providers or whatever, because the course just isn't big enough for that. The library runs training courses for Reuters databases, for example. So you should go to the library web page, and you can download training courses. Okay, so there's PowerPoint presentations on how to use DataStream. There's also presentation on how to use Bloomberg. So you just have to go to the library webpage and search for these things, and you can find them. Okay. Having said that, you can find an awful lot of free data that you don't need to use a specific tool for online as well. Okay. So hopefully you can all do a little bit of research and find good data for your assignment. Okay, so today I'm going a little bit off the flow of things in the textbook, for example. So I'm covering some concepts that are fundamental to econometrics to make sure that they're covered and that you're all familiar with them early on, rather than following the exact flow of the textbook. Okay? So one of the things we're going to cover today is when you get a report from EVs. So a lot of you have done labs already, some of you are doing labs tomorrow, but we looked at things like the p-values and test statistics, but there's other things in there aside from that. And those are goodness of fit measures. So basically they're describing how well your model fits the data. How well does it describe the data? If you have a model that predicts the returns on the S&P 500, for example, how accurate is it every day? What percentage of accuracy, or how much of the variation in the returns does your model explain? Okay, so there's a concept of R squared. So 1 is the maximum. So if your model exactly predicted the returns, you'd be very, very wealthy, and you have a very good model. And 0 means no prediction whatsoever. So it has no predictive power. So in finance, when you talk about predicting returns, you know, if you can get 10 or 12% forecastability, that's considered quite high. know, you could make quite a bit of money with something like that. You'd still have quite a bit of risk. If you've got something better than that, it becomes suspicious because it's unlikely that you're going to get something as good as that due to the efficiency of most markets. So we're going to look at model selection then as well. Okay, so one of the things is you could fit a model based on the goodness of fit, how well it describes the data, and you know, that's one possibility. And then there's other criteria that are information theoretic criteria, okay, and they're quite popular, and we're going to go through those. So in your labs, you're going to use those quite a lot. I'm going to describe what maximum likelihood is. So, yeah, people get a little bit confused about maximum likelihood, so I'm going to explain to you what it is. And we're going to look at ARMA models. Okay, so autoregressive moving average models. I mentioned that sometimes people give up on trying to use fundamental data to predict stock prices or stock returns, and instead they use a purely technical approach. So they use the series of returns themselves to try and predict the next return. Okay, so if yesterday's return has a small is positive, and today's return is likely to be positive as well because yesterday's was, so if there's positive autoregression there, then you can predict a little bit of the return in advance. Okay, and that's what these ARMA models do. You're using the history of a price series to try and predict future values. Okay, so we jump around a little bit. In these couple of lectures, we're covering things from Chapter 4 and Chapter 5 and Chapter 6 in books. Okay, so how would you decide whether something fit well or didn't fit well? So what's a goodness of fit statistic? We saw before that you have residuals, which are errors from your model. So when you subtract the prediction from your model from what you're trying to explain, there's an error there, and that's referred to as the residuals. So intuitively, you would think the smaller the error is, the better the model. Okay, but actually, you need a sum of the errors over all of the sample that you're looking at. And then the final thing is that if you just sum the raw errors, the errors might cancel out. So a good error and a bad error, or a positive error and a negative error, they might cancel each other out, and you could end up with a sum of errors that's 0, even though your average error was much bigger than 0. So you square the errors. So you end up with something called the total sum of the square errors. Okay. So when you're looking at the total sum of the square errors, how would you decide if that was good or bad? So let's say we were looking at temperature before, and temperature's in a range. Most of the time here, it's probably in a range of sort of 20 degrees or something. And if you got a value of error that was on average 100, it would be much bigger even than the range of the grid. It would be terrible. Okay, but an error of 100 when you're trying to predict something that could be in financial terms, 100,000 or 1 million a day, something like that, an error of 100 would be small. Okay, so the total sum of the square errors, you need to compare it to something else. Okay, so that's what we do when we look at the goodness of fit. You can split the total sum of the squares into 2 parts. So the part that we've explained, and the part that we haven't explained in a regression. Okay? So when you look at, for example, a variable you're trying to explain, it has variation around a mean. Okay? And the total sum of the squares around that mean are basically what you're trying to explain using your model. So what we're going to do is split that total sum of the squares into 2 parts and explain some of the squares, which is explained by the model, and the residual sum of the squares, which isn't explained by the model, which is the residuals or the forecasting area that we mentioned before. So you don't have to worry too much about this. it's a simple enough equation really. What you're looking at is 1 minus the residual sum of the squares over the total sum of the squares. So this is the variation in the variable you're trying to explain, and this is the variation in your residuals. So if your errors were 0, for example, from your model, this bit will be 0 on top here, and you'd be subtracting 0 from 1, and you get an r squared of 1. The bigger the unexplained part is, or the smaller the explained part is, the worse your r squared is going to be. Okay, so if your residuals are very big, and they actually equal the original signal, then you're explaining none of the signal. And that ratio is going to be 1. So RSS over TSS is 1, and 1 minus that is 0. You get an r squared of 0. Okay, so as I said, it's quite hard to get a very high r squared in finance outside of modeling volatility. So modeling stock returns or index returns is notoriously difficult. It's very, very difficult. Modeling volatility is easier. So you might be able to explain sort of 50 or 60% of volatility or forecast it. In which case, I mean, you get an r squared of 50 or 60% on a regression of realized volatility against some predictor equation. But with returns, you're very unlikely to get a high r squared there. You know, even sort of 5% or something will be considered good. I worked for an asset manager. They had a stock picking tool, and for some of their models, they could get up to 12% for a very specific sector, using an awful lot of factors and an awful lot of work. So even getting an r squared of 12% is quite hard to predict stock returns. Okay, so this diagram here is basically showing you what does an r squared of 0 mean. Okay, so let's say this is your line, and this is the linear regression that we ran, and we get this line, and we're trying to explain these blue points here. And actually, we're explaining we explain none of the variation in the original. Okay, so as x changes, we're not explaining any of the y values. Okay, and that's an r squared of 0. An r squared of 1 is a perfect fit. So all of the points are on the line given by your model, your linear regression model. So the errors are 0 here. Every point is on the line. The difference between the line and the points is 0 at every point. And you basically end up with no forecasting error and an r squared of 1. Does everybody understand that? You get the concept of an r squared. So it's between 0 and 1. The higher it is, the better. It means your model explains more of the variation in the original variable. Okay, so there's some problems with just using r squared. You might say, if I ask you to pick a model, or which is the best model, why don't you just use the goodness of fit? The r squared is a goodness of fit. Okay, so yeah, so there's a couple of different arguments against using r squared. But the main issue with degree is this number 2. Okay, as you add variables to your regression, there's no penalty there. So the r squared only goes one way. It never gets smaller. It will only get bigger. Okay, so if you only use r squared, you would just keep adding lots of variables to your model. They wouldn't have to be significant because you're only picking the model based on the r squared. And basically, if you've got enough random signals, you can construct anything. You can replicate anything. But it will be overfit. So what it means is that you could explain index returns perfectly for the last 4 years using maybe 1,000 different factors that you just add in, and that model would perfectly explain the index returns over the historical period. But then when you try to use it in the future, it just wouldn't work. Okay, because it was all just random and it was all just fit to that data. So an example is if I'm betting on a horse in a horse race, and the horse that wins basically has a particular number. Okay, so let's say number 4 wins the race. You know, and maybe every single race on a particular day out of 10 races, number 4 wins that race. You know, you could basically come up with a strategy where you bet on number 4 all the time. Okay, tomorrow, you know, number 4 might not win any races. Okay, it's just a spurious relationship that you found. And if you include enough factors in your model, you find these spurious things that just happen to happen. There are coincidences, and you built a model based on coincidences. And using the R-squared doesn't penalize that. So often people use an adjusted R-squared measure. Okay, what that does is it tempers the R-squared and it reduces it a bit, and it has a penalty for the number of variables that you add in to overcome this tendency to overfit. So if you're going to add in an extra variable, it has to overcome this penalty first. Okay, so it needs to add enough to the model to overcome the penalty for adding it. So that stops you from adding variables that aren't really strong variables or factors just to overfit. And that's an adjusted R-squared. And this is the equation for it here. And it basically scales, it by the size of the sample as well. Okay, so the bigger the sample is, the less likely you are to be overfitting something. It's harder to fit something to a large sample. So you're less likely to get coincidences that look statistically significant in a large sample. Okay, and K is the number of regressors. So there's still problems with using the R-squared there because it's a sort of a soft rule, and there's no distribution for R-squared. So you can't give a confidence interval for it, or you can't give it, you know, any kind of statistical significance of it. And normally in econometrics or when you're reporting results, if you say the value is X, you have to also report a confidence level with that value. So if we say the R-squared is 50% here, people might say, okay, but what's the confidence interval on it? How sure are you it's 50%? Or what's the range? You know, I want to be 95% sure that it's greater than 40%. Can you guarantee me that? And you can't calculate that for an R-squared or for the adjusted R-squared. So that's some problems with it. So normally what it's used for, you know, I would use it, for example, or you would quote it in your research, but it gives you some kind of a feeling for how much explanatory power the model has. But you won't use it for selecting factors or for making decisions. It's like information, it adds a bit of information and a bit of insight, but you don't use it for making decisions as to whether to pick a particular model or not. Okay, so there's a regression example here. In the labs, we're running a regression, and we're using the family fringe factors. So I think you're all going to have experience of running a simple linear regression. This is just another illustrative one. You know, people wonder why you might study this stuff or why you might use these, but you could actually be surprised sometimes when you come up with a problem and you pose it and you try to think of variables that might be of interest, and then you run the regression and you see that they are relevant, or they are, you know. So this one is trying to explain house prices. So it's got a model to explain house prices. Rental values. So how much money you get for a particular house when you rent it out. So some of the things are the age of the property. You know, a newer property might fetch more money. The number of bedrooms, the area per room, whether or not there's an elevator, whether or not there's a basement, car parking spaces, is there a lease attached to it or not? Oh, how far is it from a business district? How many single parent families are in the area? Okay, so that one's a bit discriminatory. It's sort of implying that a worse area has more single-parent families. And the distance to the nearest shopping centre. And yeah, the vacancy difference between the buildings. So how vacant is the building, how many empty units are in it. So before you run your regression, if you pose a problem, you would have an idea as to whether these things are good or bad. So what's good and what's bad. So a distance from the business centre, you'd expect it to be bad. A bigger distance is worse. Okay. The same with the shopping centre. The closer you are, the better they should be. So before you run the regression, you have an expectation that the coefficient will be positive or that the coefficient will be negative, depending on whether the effect of the variable is positive or negative. Okay, and this is just basically, reinforcing that. So all of these variables were significant. Okay? So when you look in e-views at the output, and you see each of these will have a parameter label like C of 1, C of 2, C of 3. You get the coefficient value, you get the T ratio. The higher the T ratio is in absolute terms, the better. So if it's positive or negative, the size of it, the size of the absolute value is what tells you whether it's significant or not. They haven't reported the p-values here because they're the same as the t statistics. So you can get a p-value from a t statistic and vice versa. So a low p-value is good, or a p-value is 0 or less than 0.05. A high one is bad, and the t ratio is the opposite. Okay. So the R squared is 0.65. So about 65% of the rental income or the rental price was determined by this regression, which is pretty good. So if somebody gave you an apartment and asked you to predict the rental income from the apartment, you could run this model. You'd ask them for all of this information and figure it all out, and then you could predict a sort of what the rental income was. So you'd be out by 35%, which is quite large. I know I wouldn't want to, if I was renting somewhere out, I wouldn't want to be out by 35% of the rent that I got. But anyway, so you can see that the things that you expect are positive, and the things that you expect are negative. Okay. So, I mean, this is just showing you that this stuff actually works. Okay, so if you want to compare between two different models, okay, so this is what we're doing in the labs. You've got two different concepts. One is a nested model and one is a non-nested model. So what I'm getting you to do in the lab is nested models. Okay, so what it means is that you add another variable to the model, you get a new, so in the labs we added in momentum, for example. You had 3 Fama-French factors plus momentum. So the previous model was nested within the new model. Okay, so you can compare whether the nested model was better or the new model was better. Okay, so when you run an encompassing test, which is what I had you run basically in the lab, you include the new variable, and you've got a number of different possible outcomes. Okay, either one of the variables is significant, or the other one, or both are, or neither are. Okay, so there are problems with these type of models sometimes. Okay, but for what you're doing, that approach is valid. So you can just add in another factor and see if it's significant in the presence of the other factors, and if it is, you leave it in. Okay? Now, in practice, there's a number of different ways of doing that, and the result that you get is path dependent. So you have stepwise regressions. So what I'm saying to you to do is to add one in and see if it's significant or not, and if it is, keep it in, and then you add another one. But what you can also do is a reverse stepwise, where you add them all in, then you pick the weakest one and you take it out, and then you run it again, and then you pick the weakest one and you take it out and you run it again. So you can see that you can do it either by making the model bigger in steps or by making it smaller in steps. And both of them have issues because there's certain combinations that they won't test. So there's a number of different factor subset selection algorithms out there. And people use things like lasso regressions and everything, but they're outside the scope of this course. But it's just to make you aware that they exist. Okay? And if ever you have a problem where you've got a very large number of factors and you're trying to pick a subset of those, you should just be aware that there's, other than just stepping through them, there's other techniques out there as well. Okay, I mentioned data mining before, and basically you're always open to accusations of data mining. In particular, if you start off and you don't have a theoretical basis for your model or for your factors. So what these guys did was correct. They sat down and they thought about what would affect rental prices. And they came up with a load of things that they thought might affect rental prices. They wrote them all down. They got the data. They included them all and they tested them. Okay? What you could do is just write a program that downloads all sorts of data and all sorts of macros. So it's quite common, you know, in economics or in finance. There's data sets available with maybe 250 macroeconomic factors or whatever. And then you could start data mining. And you can imagine if you have 250 different factors and you're looking at sort of, if you're looking at a confidence level of 95%, or you're going to have something like 10 or 12 factors that will become statistically significant just by chance, possibly. And that's data mining. So data mining is where you don't have a theoretical reason for including a factor. You just go looking around or mining to try and find things that have a relationship, possibly just by chance. And then you try and publish those, or you try and come up with some theory to explain it, or it looks like a strong result, but it's not. Okay? And even for example, the French factors, some people would accuse them of data mining. So unless you have a financial theory behind what you're doing, you leave yourself open to that accusation. Okay, so, but as I said, these guys, they've come up, this is fairly obvious. All of these things are obviously things that would affect rental income. But if they had something in here that was completely random, maybe you would think, you know, like, I don't know, something that, you know, you wouldn't expect to affect rental incomes, okay? Then maybe you would be a bit suspicious. Okay, so data mining is basically just searching, and you're just looking for a statistical relationship. So you can code all of this up, and you can make it automated, and you can just kind of have loops that try lots of things and run regressions, and keep things in that are significant, and remove things that aren't significant. And you could almost automate papers. So you could automatically write papers. And some people do similar things to that. Okay. So that covered data mining. Multicollinearity, that's an issue with linear regression estimation. If your variables are correlated to each other, like you use in your regression, it causes problems. So you can imagine if you basically took one variable and you divided it by 2, you'd have two variables in your regression. Okay, and each of those variables would be completely correlated with each other. So if you just divided it by 2 and included a half and a half. Imagine let's say you're a program and you're trying to figure out what coefficient do I give each of them. Okay, maybe you give them half of the original coefficient each. But maybe you give one of them double and the other one 0. Or maybe you give one of them minus a half and the other one plus 1.5. What binds you? You don't. It's not solvable. Okay, so it becomes, and then it becomes even more difficult because you never have that situation where you've got a half and a half. Normally you've got variables that are highly correlated, and then they have a noise term as well. Each of them does. Okay? Or they have some other signal in there. Each of them, but they're also highly correlated. And that becomes even trickier because what the program can do is basically cancel out and use a linear combination of each of the two factors to cancel out the original signal. And what you're left with then is just the noise, which is a completely random signal, which may just randomly be significant. Okay, so you could end up, whenever you see variables that are highly correlated, sometimes you see one of them gets a positive coefficient and the other one gets a negative coefficient. And actually what the regression algorithm is doing is trying to create a signal. It's trying to create a new signal. So you've given it the freedom to subtract these from each other and create a new noise variable. And it's got some freedom in how to create that noise variable to try and make it look significant. So multicollinearity is an issue. What people do is they test their variables first to see how correlated they are. And then there are solutions to multicollinearity, such as, again, I mentioned lasso regression before, but you can limit the size of any one coefficient. Okay, so it sort of constrains. I said nothing was binding the regression or making it decide what to give to each. But you can force it or constrain the size of the coefficient on each of those, and it gets around these multicollinearity issues. Okay, so if you have multicollinearity and you just ignore it, you could get a very high R squared, but the individual coefficients will have high standard errors. And the regression becomes very sensitive to small changes in specification, and the confidence intervals for the parameters will be very wide. So your significant test might give inappropriate conclusions. So you might start saying each of those two variables is not significant, and you remove them from your regression. If you included one on their own, you might find it's highly significant. Okay, so they're just things to be aware of. So the easiest way to measure multicollinearity is just to check the correlation. So you're all probably familiar, hopefully, with correlation matrix. The diagonals here, he's got a hyphen in there, but they should be 1. Okay, so x2 is, has a correlation of 1 with itself. x3 is a correlation of 1 with itself. x4 is a correlation of 1 with itself. And if we were looking at this, we'd say, oh look, x4 and x2 have got 80% correlation. So they're very similar factors. So then we'd be aware that multicollinearity might be an issue there. Ideally, your factors should be orthogonal, which means they're not correlated to each other. Okay, so another solution to multicollinearity, and something that I've used in the past, is something called principal components analysis. And you can run a principal components analysis on a set of factors. And what it does is it pulls the main or the principal components out of those factors. So if they have something in common, it just takes out what's common from all the factors, and it assigns that to a new single factor. And it does that for all the orthogonal factors that are available in the data set. So you end up with something that's completely fixed for multicollinearity. The problem is that you no longer have the same factors. You have an artificially constructed set of factors, and you can no longer interpret the coefficients on those in the same way you could previously. So, what you find is that whereas before maybe the market had a beta of 1 in your regression or something, suddenly factor 1 has a beta of 1, and factor 1 isn't just the market. It's like point something times the market plus point something times another factor plus. It becomes harder to interpret. People have used PCA. There's a guy called Ed Thorpe that he used to run a hedge fund, Newport Capital Partners, and he made an awful lot of money doing statistical arbitrage, and he did PCA on a set of equity factors, a large set. And they made a lot of money for years, but then everybody started doing similar things, and the returns dropped off, it becomes less. And that's what happens. If you discover something that works, you make a lot of money, and then you're reinvesting your own money, so you're sort of working against yourself. And also, other people figure out that you're making a lot of money. You've got a broker, or you've got, and they try to figure out what you're doing, and then they try to copy you, and you have more competition. And in the end, everybody's doing this, or there's an awful lot of people doing it, and the profits disappear. And then something else becomes profitable, and people will start doing that. Okay. So, yeah. There's some traditional approaches to solving multicollinearity. You can run a type of regression called a ridge regression, which can tackle some of the problems of multicollinearity, the principal components. So the comment here, these usually bring more problems than they solve. It's not necessarily always the case, but whenever you use something, you need to be very careful. Everything we saw with the CLRM, it comes with a set of assumptions that have to hold. And whenever you use a tool, it has to be the appropriate tool to use. Okay? And if you're ignoring something, there could be some big reason why you shouldn't be doing that. Okay, and some people say just ignore multicollinearity, if the model is okay otherwise. So you can see a lot of this econometric stuff, it's not black and white. So it's a bit more like cooking, where they say add a little bit of this and a little of that, and oh, that worked out well, let's do that again next time. And it's not a pure science. So people have techniques that they use and sort of recipes that they follow, and they work, so they stick to them. Okay, the easiest way, you could drop one of the collinear variables, but the problem is then that you could lose some information in that factor. And that isn't common information, and you're throwing it away. And so normally, if you're including a separate factor, it's because it is separate. You thought this was a separate factor, and it had something to add. If it turns out it's highly correlated to something else, the part of the factor that's highly correlated, maybe you want to remove that, but there could still be something in the factor that you want to leave in there. You can transform the highly correlated variables into a ratio. So there's different ways of handling it. For your coursework, I would say, if you can run the correlation matrix and report that, and just address the issue whatever way you see fit. Okay, so if you say, if I include it in, my standard errors are bigger, but all the variables are still significant, and I've still got a better R squared, so I'm just going to stick with this model, then that's fine. Okay? Just once you address it, and you show that you've thought about it, and you've analyzed it, then that's fine. Okay, so we'll take a break there, and I'll come back about